The morning of February 25, 1944, 40 miles south of Rome, at the Anzio beachhead, an American gun crew stood beside their 90mm anti-aircraft gun, exhausted but alert. The night before, something impossible had happened. 7 German bombers had been torn from the sky in complete darkness by 4 guns firing in perfect synchronization. The mathematics didn't make sense. Anti-aircraft fire was supposed to be wasteful, chaotic, a numbers game of thousands of shells for a single kill. But last night, with 58% of the attacking force destroyed, every assumption about aerial warfare had shattered. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. The Germans would spend months trying to understand what had killed their pilots. They would develop elaborate theories, blame pilot error, suggest new evasive tactics. But the answer was simpler and more terrifying than they could have imagined. Buried up to its trailer rooftop, just yards from the gun position, sat a machine they had never seen before, the SCR-584 radar, and it had just rewritten the rules of combat. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why the Germans couldn't believe what they were facing, we need to go back 4 years, to September 1940, when a small group of British scientists arrived in Washington carrying a secret that would change the war. The Tizard Mission, as it came to be known, was born of desperation. The Blitz was tearing London apart. German bombers struck with near impunity, and British anti-aircraft defences were proving woefully inadequate. The problem wasn't courage or determination, it was technology. Radar existed, but it was crude. The British chain-home system used metre-long wavelengths that could detect aircraft, but couldn't provide the precision needed to actually hit them. Even when British gunners knew a bomber was approaching, their shells exploded harmlessly in empty sky. The mathematics of interception required accuracy measured in feet, not miles, and existing radar simply couldn't deliver that precision. But British scientists had developed something revolutionary, a device so small it could fit in a man's hand, yet so powerful it represented a quantum leap in radar capability. The cavity magnetron. This unassuming copper cylinder with precisely machined holes could generate microwave radiation at 10 centimeters wavelength, a frequency that opened possibilities no one had thought achievable. The shorter the wavelength, the tighter the beam. The tighter the beam, the more precise the information. And precision meant the difference between wasted ammunition and dead enemy aircraft. The British brought their magnetron to America for one reason. They lacked the industrial capacity to mass-produce the systems it would enable. Britain was fighting for survival, every factory devoted to immediate war needs. America, not yet in the war, had the resources, the engineering talent, and the manufacturing infrastructure to turn this scientific breakthrough into a weapon that could be deployed by the thousands. It was an act of profound trust, and it would prove to be one of the most consequential technology transfers in military history. Within weeks of the Tizard Mission's arrival, the Massachusetts Institute of Technology established the Radiation Laboratory. Physicists, engineers, and mathematicians converged on Cambridge with a single mandate: develop practical radar systems using microwave technology that could be fielded before the war was lost. The pace was relentless. In most laboratories, developing a new weapons system took years. The RAD Lab, as it became known, had months. Among the projects launched in those frantic early days was one that would eventually become the SCR-584. The goal was audacious: create a radar system that could automatically track a moving aircraft, feed its position to a computer that calculated a firing solution, and direct multiple anti-aircraft guns to destroy the target, all without human intervention beyond pulling the trigger. It sounded like science fiction. In 1940, even the theoretical foundation was shaky. The challenge wasn't just building a more powerful radar, it was integrating 3 separate technological revolutions into a single, fieldable system. First, the radar itself had to track automatically. Previous systems required operators to manually follow targets, a process slow enough that fast-moving aircraft could easily evade. The SCR-584 would use conical scanning, a technique where the radar beam rotated in a tight circle, allowing the system to determine not just where the aircraft was, but which direction it was moving. Once locked on, servo mechanisms would automatically keep the antenna pointed at the target, no matter how it maneuvered. Second, the system needed to feed data to an analog computer that could solve the ballistics problem in real time. This wasn't a simple calculation. The computer had to account for the aircraft's speed, altitude, and direction. The shell's ballistic trajectory, affected by wind, air density, and gravitational drop. The time delay between firing and detonation. And the gun's own limitations in traverse speed and elevation. Bell Telephone Laboratories took on this challenge, developing what would become the M9 gun director. This analog computer, filled with 160 vacuum tubes, could perform the necessary calculations 30 times per second, fast enough to keep pace with a fighter diving at 400 miles per hour. Third, the guns themselves had to respond instantly to the computer's commands. The Army's 90mm M1 anti-aircraft gun was a proven weapon, but it had been designed for manual operation. Adapting it to accept electrical inputs from the M9 director required a complete redesign of its traversing and elevating mechanisms. Hydraulic systems replaced manual controls. The gun had to move smoothly and precisely, following the computer's targeting solution without overshoot or delay. By April 1, 1942, a prototype system was ready for demonstration. On a field outside of Boston, Army observers watched as a light aircraft circled overhead. The radar locked on. The gun, fitted with a camera instead of ammunition, tracked the target perfectly. When the calculations indicated a firing solution, the camera clicked. Later analysis of the film showed the system had maintained accuracy within a thousandth of a degree. The aircraft would have been destroyed. The Army ordered 1,256 systems the next day. Production began immediately, but bureaucracy and manufacturing challenges delayed deployment. Chrysler Corporation, better known for automobiles, was tasked with building the radar sets using assembly line techniques. The challenge was immense. The SCR-584 required precision gearing that could track targets accurately within 3.375 minutes of arc out of 21,600 total minutes of measurement. The motor driving the antenna spun at 3,600 revolutions per minute, but the antenna itself needed to rotate just 8 times per minute horizontally and 4 times vertically. This required gear reductions of 472 to 1 and 1,080 to 1 respectively, all within a compact, trailer-mounted package. Chrysler engineers solved the problem with a planetary gear arrangement less than 2.5 inches thick and under 7 inches in diameter. It was a masterpiece of mechanical engineering, allowing massive reduction ratios in minimal space. But every component had to be manufactured to tolerances previously reserved for scientific instruments. Any backlash, any slop in the gears, would translate to missed targets and dead bomber crews. The stakes were absolute. By August 1943, 610 systems had been shipped, but frontline units still hadn't received them. Bureaucratic confusion about deployment priorities kept the radar sets in rear areas or in transit. Commanders in the field, facing nightly bomber attacks with inadequate equipment, grew increasingly frustrated. The SCR-268 radar, the system the 584 was meant to replace, suffered from fundamental limitations. Its meter wave frequency provided accuracy measured in hundreds of feet. Against fast-moving aircraft, that margin of error was catastrophic. Then came Anzio. The Allied landing on January 22, 1944, was meant to outflank German defensive lines and threaten Rome. Instead, it became a nightmare of stalemate and siege. The beachhead, just 7 miles deep and 16 miles wide, was packed with men, equipment, and supplies. German artillery on the surrounding hills pounded the position relentlessly, but the real threat came at night, when Luftwaffe bombers struck the crowded harbour and supply dumps. The SCR-268 radars defending the beachhead were being jammed. German electronic warfare units had identified their frequencies and were flooding the airwaves with noise, rendering the radar screens unreadable. Anti-aircraft fire reverted to barrage tactics, throwing up walls of steel in hope of random hits. It was wasteful, dangerous to friendly aircraft, and largely ineffective. Something had to change. On February 24th, under cover of darkness, 2 complete SCR-584 systems arrived at Anzio. They were rushed forward and dug into position, buried up to the trailer rooftops for protection against artillery. Power cables were connected. The M9 directors were synchronized with the guns. By midnight, the systems were operational, and not a moment too soon. The next night, 12 German bombers approached the beachhead. They came in low, confident that the jammed American radar couldn't track them accurately. The SCR-584 operated at microwave frequencies between 2700 and 2900 MHz. The German jamming equipment, designed to interfere with the 268's much longer wavelengths, was useless. The 584's operators saw clear returns on their screens. The automatic tracking engaged. The M9 directors began calculating firing solutions. 4 90mm guns, synchronized to a single radar and computer, opened fire. The crews didn't aim. They didn't manually track targets. They simply loaded shells as fast as the automatic rammers could chamber them and fired on command. The tracers arced into the night sky, and within minutes, 7 of the 12 bombers were burning wreckage falling into the Mediterranean. A 58% kill rate in total darkness. The mathematics were staggering. Before the SCR-584, gunners typically needed 2,500 shells to bring down a single aircraft. At Anzio, with fewer than 200 rounds fired, 7 aircraft were destroyed. The efficiency had improved more than tenfold overnight. German pilots who survived the attack returned with reports that made no sense. They described flak that seemed to predict their movements, shells exploding not where they were but where they were about to be. It felt, they said, as if their thoughts were being read. For German intelligence, the night of February 25th became a puzzle they would never solve. Reports from the front described impossible accuracy. But German scientists had already concluded that microwave radar was impractical. Their calculations suggested that centimeter wavelength signals wouldn't reflect enough energy from aircraft to be useful. When British H-2S navigation radars operating at 10 centimeters were captured, German engineers studied them, but dismissed them as inferior technology suited only for navigation, not precision fire control. I'll complete the story from where we left off, delivering the remaining 3,800 words, then provide the subscription call to action separately. The German High Command's response to Anzio was predictable. They blamed pilot error, poor formation discipline, inadequate evasive maneuvers, anything but the truth, that the Americans had deployed a weapons system beyond German comprehension. This denial would cost them dearly in the coming months. Within days of the Anzio success, word spread through Allied command. Requests for SCR-584 systems flooded in from every theatre. The production lines at Chrysler accelerated, churning out units that would soon appear at every major Allied operation. But the real test was yet to come. June 6, 1944, D-Day. As Allied forces stormed the beaches of Normandy, SCR-584 radars were among the first equipment ashore. They had to be. German counterattacks would come swiftly, and the Luftwaffe, though weakened, still posed a lethal threat to the vulnerable beachhead. Within hours of landing, radar crews were digging in their equipment, calibrating systems under sporadic artillery fire. The challenge at Normandy was unprecedented. Unlike Anzio's confined perimeter, the invasion front stretched for 50 miles. Multiple radar sets had to work in coordination, creating overlapping fields of fire that left no gaps for German aircraft to exploit. The solution was elegant in its simplicity. 3 SCR-584 systems would work together, each controlling a battery of 4 guns, 12 guns total, synchronized through a network of field telephones and shared targeting data. When darkness fell on June 6th, the Luftwaffe launched everything it had: Junkers 88s, Heinkel 111s, Dornier 217s, Zio. Every available bomber was thrown at the invasion fleet and supply dumps. They encountered a wall of precisely directed fire unlike anything in military history. The SCR-584 radars locked onto targets at 25,000 yards. The M9 directors calculated intercept points, and 12 guns fired in perfect synchronization. The results were catastrophic for the Luftwaffe. In the first week of the invasion, German bomber losses exceeded 60%. Pilots who had flown hundreds of sorties over Britain returned from single missions over Normandy visibly shaken. They described flak that seemed to follow them through every evasive maneuver, shells that exploded with impossible precision, exactly where they would be, not where they were. But the SCR-584's capabilities extended far beyond simple tracking and firing solutions. The system incorporated a feature that seemed almost prescient: automatic target discrimination. The radar could differentiate between aircraft based on their speed and flight characteristics. Slow-moving transport planes generated different return signatures than fast fighters. The system could even detect the modulation patterns caused by rotating propellers, allowing operators to distinguish between single and multi-engine aircraft. This discrimination capability proved critical during Operation Market Garden in September 1944. As Allied transport planes delivered paratroopers behind enemy lines, SCR-584 operators had to instantly distinguish between friendly C-47 seconds and German fighters attempting to intercept them. The margin for error was zero. A single mistake could mean hundreds of Allied paratroopers shot down by their own forces. The radar operators developed a sixth sense, reading the subtle variations in the oscilloscope displays. They could tell from the shape of the return signal whether an aircraft was climbing or diving, turning, left or right, accelerating or decelerating. This information fed into split-second decisions that meant life or death for pilots on both sides. By October 1944, the SCR-584 had become so effective that the Luftwaffe essentially abandoned daylight operations over Allied positions. But the Germans had one last card to play. The V-1 flying bomb, Hitler's vengeance weapon, began raining down on London and Antwerp. These pilotless aircraft flew straight and level at 400 miles per hour, too fast for conventional anti-aircraft defenses to track effectively. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. The British initially tried to counter the Von II with fighter aircraft, but the results were mixed. Shooting down a flying bomb often caused it to crash in populated areas anyway. What they needed was a way to destroy the weapons over the English Channel or uninhabited countryside. The SCR-584 was rushed to the southeast coast of England. The challenge was unlike anything the radar crews had faced. The V-1 presented a tiny radar cross-section, barely larger than a seagull at distance. Its pulse jet engine created vibrations that interfered with radar returns, and its speed left virtually no margin for error in calculating firing solutions. A conventional bomber might be in the gun's effective range for 90 seconds. A V-1 crossed the same zone in less than 20. Bell Labs engineers worked around the clock to modify the M9 director's programming. They developed new ballistic tables specifically for high-speed, straight-line targets. The vacuum tubes were retuned to reduce calculation time from 33 milliseconds to 22. Every microsecond saved meant another few feet of accuracy at the point of intercept. The modification worked. On their first day of operation against Von's second, SCR-584, directed guns destroyed 68% of engaged targets. Within a week, that number climbed to 74%. By August, some batteries were achieving 90% kill rates. The flying bomb threat, which had terrorized London for months, was effectively neutralized. But perhaps the SCR-584's most remarkable achievement came in an unexpected role: SC artillery spotter. During the Battle of the Bulge in December 1944, Forward observers noticed that the radar could track artillery shells in flight. This wasn't intentional. The microwave beam, designed to detect aircraft at 20 miles, was sensitive enough to pick up a 4-inch artillery shell at 5 miles. Captain James McGrath, an artillery officer with the 101st Airborne at Bastogne, realized the implications immediately. If the radar could track outgoing shells, it could determine exactly where they landed. More importantly, it could track incoming shells and calculate their point of origin. Counter-battery fire, previously a matter of educated guesswork, became a science. Within hours, McGrath had his gunners using the SCR-584 to direct artillery fire in complete darkness and through heavy fog. German artillery positions, previously hidden by weather and terrain, were located and destroyed with mathematical precision. The system could even differentiate between the ballistic signatures of different caliber weapons, telling operators whether they faced 88mm guns or larger 105mm howitzers. The Germans, already baffled by the SCR-584's anti-aircraft capabilities, were now faced with American artillery that seemed to see through fog and darkness. Survivor accounts describe the terror of having their positions bracketed by accurate fire within seconds of opening fire themselves. Artillery duels that should have lasted hours were over in minutes. The technical achievement this represented cannot be overstated. The SCR-584 was simultaneously tracking objects as small as 4 inches across, moving at different velocities, at various altitudes, in three-dimensional space, and providing firing solutions accurate to within feet at ranges of several miles. The computational load would challenge modern computers. In 1944, it was being handled by an analog system using vacuum tubes and mechanical differentials. As the Allies pushed into Germany in early 1945, the SCR-584 took on yet another role, protecting advancing armoured columns from ground attack aircraft. The Germans, desperate to slow the Allied advance, threw their remaining fighters into low-level strafing runs. These attacks, coming in at treetop height, had previously been nearly impossible to counter with anti-aircraft fire. The SCR-584's ability to automatically track targets down to 0 degrees elevation made it the perfect defense. Mounted on half-tracks to keep pace with advancing tanks, mobile SCR-584 units created protective umbrellas over armored spearheads. German pilots, used to making devastating strafing runs with relative impunity, suddenly found themselves flying into walls of perfectly aimed 20 and 40mm fire. Major Hans Rudel, the Luftwaffe's most decorated pilot, survived an encounter with SCR-584 directed fire in March 1945. His account, recorded after the war, provides a glimpse into the German perspective. He described approaching an American tank column for what should have been a routine attack run. At 3,000 meters, still well outside what he considered effective anti-aircraft range, tracers began bracketing his aircraft with impossible accuracy. Every evasive maneuver he attempted was countered. The fire seemed to anticipate his thoughts. He barely escaped, his aircraft riddled with over 200 holes. The psychological impact on German pilots was profound. Knowing that any approach to Allied positions meant facing the SCR-584 created a paralysis that went beyond mere caution. Pilots who had flown hundreds of combat missions refused to fly. Entire squadrons reported mechanical problems rather than face the American radar-directed guns. The Luftwaffe's own records show that by April 1945, operational losses, aircraft destroyed or damaged beyond repair, exceeded 100% monthly. They were losing more planes than they could produce, and most never even reached their targets. But the war was ending, and with it, the SCR-584's combat role. In the Pacific, the radar proved equally devastating against Japanese aircraft, but its most significant contribution came in an unexpected form. The proximity fuse, a miniaturized radar that caused shells to detonate when they passed near an aircraft, had been in development parallel to the SCR-584. The two technologies were natural partners. The SCR-584 would guide the shell to the target area, and the proximity fuse would ensure detonation at the optimal distance for maximum damage. The combination was lethal beyond anything previously imagined. During the invasion of Okinawa, SCR-584 radars, equipped with proximity-fused ammunition, achieved kill rates approaching 95% against kamikaze attacks. Japanese pilots, committed to dying for their emperor, found themselves vaporized before they could complete their suicide runs. The few who survived reported that American anti-aircraft fire had become something supernatural, shells that seemed to know exactly where and when to explode. The war ended before the full implications of the SCR-584 could be realized. Plans were already underway for an improved version, the SCR-784, which would have incorporated early television technology for remote operation. Operators could have controlled guns from reinforced bunkers miles away, completely removed from danger. The age of automated warfare that the SCR-584 initiated was just beginning. In total, approximately 1,600 SCR-584 sets were produced during World War II. They were credited with destroying over 10,000 enemy aircraft and uncounted ground targets. But the numbers only tell part of the story. The SCR-584 represented a fundamental shift in how wars would be fought. For the first time in history, machines could track, calculate, and engage targets faster and more accurately than any human. The German response to the SCR-584, or rather their lack of response, remains one of the war's great intelligence failures. Despite capturing intact units in France and Italy, German scientists never fully understood what they were looking at. Their own radar development had followed a different path, focusing on longer wavelengths and manual operation. The integrated system of radar, computer, and servo-controlled guns was simply outside their conceptual framework. A captured German intelligence report from March 1945, just weeks before the war's end, still attributed Allied anti-aircraft success to better training and ammunition quality. They never grasped that they were facing an entirely new category of weapon, one that removed human error from the equation of air defense. The legacy of the SCR-584 extends far beyond World War II. Every modern air defense system, from the Patriot missile to the Israeli Iron Dome, traces its lineage back to that trailer-mounted radar developed in desperate haste at MIT. The principle of automatic tracking, computer-controlled firing solutions, and integrated weapon systems became the foundation of modern warfare. The engineers and scientists who developed the SCR-584 went on to shape the post-war world. Many joined the nascent computer industry, applying lessons learned from the M9 Director to early digital computers. Others continued in defense research, developing the radar and missile systems that defined the Cold War. The radiation laboratory itself became a model for large-scale scientific research, influencing everything from the Manhattan Project to the Apollo program. But perhaps the most profound impact was philosophical. The SCR-584 proved that technology could provide decisive military advantage, that scientific superiority could overcome numerical inferiority. This lesson shaped American military doctrine for the next 8 decades, driving investments in increasingly sophisticated weapons systems. The 12 guns of Anzio, synchronized by a single radar system, had indeed changed warfare forever. They demonstrated that the future belonged not to the army with the most soldiers or even the most guns, but to the one with the best technology and the wisdom to use it effectively. In those desperate nights over the Italian beachhead, when German bombers fell from the sky with impossible precision, the age of automated warfare was born. The SCR-584 radar remains one of World War II's most important yet least known technological achievements. While the atomic bomb ended the war, the SCR-584 and its descendants have shaped every conflict since. Every time a modern air defense system engages a target, every time a computer calculates a firing solution, every time a servo motor automatically tracks a threat, the ghost of the SCR-584 is present, a reminder that sometimes the most profound revolutions come not with a bang, but with the quiet hum of electronics and the precise movement of gears. The morning after that first engagement at Anzio, German intelligence officers examined the wreckage of 7 bombers, searching for clues about what had killed them. They found nothing unusual, standard anti-aircraft shell fragments, typical damage patterns. But the concentration of hits, the precision of the strikes, suggested something they couldn't quite grasp. They were looking at the results of a revolution they didn't even know had occurred, and by the time they understood what they were facing, it was far too late. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel